Okay, in this video I'm going to be continuing on from bending. We haven't done bending for a while, so it's going to be we're going to start again from scratch and try and go through the principles. What we're going to be focusing on today is we're going to be focusing on bending moment, free body diagrams, shear force diagrams, bending moment diagrams. Just to quickly recap, so a force can be described as a push, pull or twist. That's a common definition for a force. We know that force is mass times acceleration, but that can lead to a bit of a cycle of definition. So if we need to define a force, a push, pull or twist is a commonly used definition. Now, if we're talking about something that's being squeezed, what term would we use for that? Compression. If something's being stretched, what term? Tension. Okay, so as trusses, they're always in tension or compression. They're what we call axial forces. The forces run along the axis. If you have any part of a truss, let's say if I draw this Warren truss here, and I tell you there's a force mid-span like that, what will happen is it will no longer be in tension or compression, it won't be an axial force. It'll start to bend and the thing will break, because trusses are not designed for bending. Trusses are only designed for axial forces. Okay, it's also worth talking about twists. So twists are torsion. We don't really worry about torsion in this course. That's more a university level concept, right? So we're aware of the concept of torsion, that things when they're being twisted, that's a force and that's torsion. But what we want to focus on today is we want to focus on shear and bending. And so typically, shear and bending, they occur when the force is not axially applied, but it's transversely applied. Or another way of saying that is, so normally an axial force runs parallel to the beam, whereas a bending and shear occur when the force is perpendicular to the beam. Now, to describe the first one, shear means when we have parallel layers sliding past each other. Yeah? So in this case, we can imagine that at some point in this beam, we have a force that's pushing this one down and this one up. Scissors are the quintessential example that we think of, or a metal shear. So if you've seen sheet metal being cut, maybe in year 7 or 8, probably year 8, that you might be familiar with a metal shear. Another example of shear that we will look at, we may have already looked at with you guys, but just if you haven't seen this before, is if I have 3 pieces of metal. I have a piece of metal A, B, and C. Let's imagine something like I'm towing a boat, and done 2 B's. Okay, my boat is on point C, the car is on this side, and to hold these pieces of metal together, I drilled a hole through the middle, and I put, a nut on each end. Right? And so let's say it's, it doesn't matter where the threaded section starts. The point is that through this material, A wants to go this way, B wants to go this way, C wants to go the same direction as A. What's happening is that this bolt is being dragged in 2 different directions. At this location here, that dotted line, you can imagine that at that cross-sectional area of the bolt, it's being dragged that way by A and that way by B. And then down here, it's happening again. We're getting that side dragged by B and that side dragged by C. So we can imagine that this is being cut in half. That's when we think of shear. Now that applies for beams as well. And generally, generally that's not a huge design consideration for concrete beams, for example, or steel beams. Shear is usually not the main consideration. There are times though where we are concerned, and what happens is if we have a big concrete slab, and if I was more prepared I'd have a picture ready to go, but if you have a concrete slab, especially in places like garages, in car parks, what you might have is you might have columns spaced throughout the middle to support the concrete slab. And if this is my big concrete slab, it's not a great picture here. What can happen is that this concrete column can just punch through the slab. And that's a shear failure, it punches through. Now to prevent that, what they do is they create a shear pad underneath it. So in cross section it looks like this. cross-section, I guess, at a distance. So that's our slab, and then we have a shear pad, and then we have the top of the column. And the idea is that the shear, if it's really high here, we've got more material, and then, so if the shear force is very high here, it's got thicker material, and if it's lower there, we have less material, and we can go back to what we need. So I will show some photos later of why car parks have shear pads. We don't really need to worry about that. The other aspect is, and I'm not going to go into too much detail here, is that because it's not really part of the HSC course, I've gone through this with my class in a little bit more detail, but the concept is that we actually have vertical pieces of steel called stirrups, and that just holds the steel in concrete together. And if we know that the shear force is going to be higher at one location than the other, we can add more steel, we can add more stirrups where it's needed. If we know that we need more, usually we need more on the columns. This is a bad example. This one needs even shear force diagram. But the point is we can add more stirrups, we can add more vertical pieces of steel where we need more support for shear. Okay, so that's why we have shear. The next concept we're going to talk about quickly is bending. Now when bending, we've talked about this in another video already, but when we bend something, is this top half being squashed or is it being stretched? Squashed. This dot, these two dots, they're closer together than those two dots. Right? A and B are closer than C and D. Right? So that means this is being squashed, so that means it's in compression. In the bottom, it's in tension, exactly right. Okay, somewhere in the middle of that, it's neither in tension nor compression. This is what we call the neutral axis. There, at that line, it's neither in tension nor compression. Now, what that means is that if you were to take a section of this and measure these forces that are acting on it, we'd say there's a lot of compressive force at the top, and we'd say there's a lot of compressive force on the bottom, a lot of tensile force on the bottom, and somewhere in the middle there's no force. And if we were to take what is the force like there, well, here there'd be some compression, but not as much as above. So it'd be there, and if we look at this point, we'd say, well, there's some tension, but not as much as above. And if you join those dots, you'll get a graph of force that looks like this. The compressive force is very high at the top of the beam and very low at the bottom of the beam. That's what's going on there. Now, the thing is, we always talk about in our equations, we always use this formula here. The sum of the force, the sum of the moments equals 0. We also use some of the forces. Now, that's important, that's true, as long as the beam is strong enough to hold together. What we as engineers want to do is we want to ensure that that remains true, that formula is true, that we design things that are big enough that it's true. But what's happening is inside the beam, there is internal forces, and if those internal forces are more than what the beam can provide, it's going to break. So yes, the left-hand side and the right-hand side are always going to balance so that they're going to add up to 0, but how much force is going on really matters. How I like to think about this is, headphones out please, how I like to think about this is I like to think about if you have an arm wrestler, if you have two kids in kindergarten arm wrestling, or you have two professional wrestlers arm wrestling, if they're both stuck and they're both in an equilibrium, neither the children nor the wrestlers are winning, you might say, well, the sum of the forces are equal to 0. But the difference of those forces in those people's arms is enormous. Right, the kindergartners, they couldn't provide the same amount of force as those two professional wrestlers because their arms just aren't strong enough. If you put that same amount of force on those kindergartners' arms, their arms would just break. Yeah, they would snap out. There was actually a football player, I'll show you a video maybe later, of a football player just getting his arm broken from arm wrestling. Also there's the movie The Fly, where he breaks that guy's arm. Yeah. Okay, so what we're going to look at is how much is going on here. Now, just to reiterate that point one more time. So if I had a rope and it was in tension, and you'd say, well, okay, the force was equal to 0, or I had a big strong chain and the forces were being balanced, you'd say, well, some of the force is equal to 0. But it's how much force. The tug of war between two kindergartners and the tug of war between two squads of army men are very, very different. Even though they're both equal to 0, the point is that there's an internal force and it's whether or not the rope is strong enough to provide a reaction force to support that force that matters. Okay, that was a very long intro, and we've got a lot to work on, so let's have a look. What we're going to look at here is we're going to start with this being, and we're going to start drawing these diagrams. Later I'll talk about why we care about these diagrams, but for the moment we just want to start drawing these diagrams. So the first thing we're going to do is we're going to draw what's called a free body diagram. That's pretty much done for us already by Copeland on that side. So what we have here is we have our diagram that looks like this, and it's 2 meters here, and it's 2 meters here, and the load is 40 kilonewtons. So we can kind of see a little bit of the answer, but what is the reaction on each side going to be in this case? 20. We know that because it's symmetrical. That's really important, right? You don't have time to calculate reactions when it's supposed to be obvious. If the thing is set up to be loaded symmetrically, we can just apply the reactions. We don't have to do all of the reaction calculations. Really important. Okay, the next thing is I've actually given you a formula previously to find the maximum bending moment. And we said that was FL on 4. We're going to have a look at that. So in this case, we're going to say F is, what is F in this example? 40 kilonewtons. Okay, what is L in this example? Sorry? 4 meters, exactly right. It's the distance between the spans, so it's going to be 4 meters. Right. What we're going to calculate is what the maximum bending moment's are. But before we get to that, we're going to look at shear force diagrams. We're not going to go straight to the bending moment. We're going to look at a shear force diagram first. Now, we've got a couple of points that we're interested in. We want to look at point 1, point 2, and we're going to look at mid-span. Okay. So how I like to do this is I like to tell a story. So this is our free body diagram. I'm labeling that free body diagram. Now I'm labeling this one shear force diagram. Okay, once upon a time, there was a force of 20 newtons up. And then nothing happened for a while. The diagram walked along for 2 meters, and then suddenly a 40 came along, and it was 40 down. Ooh, it was a scary time for the shear force diagram, being in the negative. But he kept on walking for 2 more meters, and then suddenly everything worked out and it was back to 0. He added 20 newtons and it was back to 0, 20 kilonewtons and back to 0. So let's have a look at our diagram. So it's 2 meters in each of these blocks. And how tall is it? Well, it's 20 up, and 40 down there. Now, that is our shear force diagram. As we can see in this diagram, the maximum shear force that we have in any location is 20 kilonewton meters. Yeah? And that's what we're going to design for. The stirrup spacing is going to be evenly spaced based on on 20 kilonewton meters. Yeah? Usually we have to add some stirrups anyway. Usually stirrups are not a huge problem unless we have slabs, and we'll worry about that later. Even then, you don't need stirrups and slabs. Anyway, you guys aren't concreters, you're not going to call me on that one. Okay, so then what we're going to do is we're going to jump straight into the bending moment diagram. Bending moment diagram. Now, I'm only going to do the calculations once or twice because normally I don't do the calculations at every point. Okay, so what we're going to do to start off with is we're going to say what is the moment that is going to be on the left at this point here. Now, we know that it's equal to 0 at any location. You know, we're going to come back to this one, but I'll quickly say it just to not let people hang. The point is it's going to be 0 moment at this location. Now, we're going to say that the total is 0 at every location, but in this case, because there's no left-hand side, we could say that the left-hand side is 0. Well, that means everything else on the right has to add up to 0, right? And that's kind of the calculation we do when we find those reactions, is we're saying the sum of the moments at relative to point A are going to be equal to 0. Now, so I'm just going to write that that's 0 here, right? Now, to say if you're guessing, that's going to be the same here. What we can look at now to start off is we'll look at the mid-span. Now, we could look at the mid-span as either the left-hand side or the right-hand side. So I'm going to call this point M for mid-span. So if I say here, the sum of the moments measured from point M equals 0, but we know that at any point it's going to be 0, assuming the thing is holding together and it's not breaking, it's going to be 0. But I'm going to say it's equal to a left-hand side plus a right-hand side. Well, what does the left-hand side of this diagram look like? The left-hand side of this diagram looks like this. We've got 20, 2 meters long, and 40. And we're measuring from M. Now, if we're measuring from point M, so we're going to say 0 equals, well, first of all, we've got 40, we've got a force of 40. It's not positive or negative. Why is it not positive or negative? Does it have a turning clockwise that's positive or turning clockwise that's negative? I said it doesn't have either. Why? I can't hear you, sorry?
There's no distance.
Exactly, because there's no distance. The distance to M is 0. So we could almost ignore that in our diagrams. And then we have one other force. We have this force here of 20, and it's 2 meters away. I'm going to write minus 20. Now, is it going clockwise or anti-clockwise?
Anti-clockwise?
Is that how a clock turns?
Yes, clockwise.
Okay, so it's going to be positive 20 times 2. So what is our bending moment going to equal? Oh, so this is our left-hand side, not 0. Left-hand side equals LHS equals 40, right? Now, it's 40 kilonewtons times a meter, so it's going to be 40 kilonewton meters. Now, I am going to keep it that for the moment, but it's worth knowing that normally I will always work, unlike Copeland, I work in times 10 to the 6 Newton millimeters. Yeah? I convert kilonewton meters to times 10 to the 6 Newton millimeters. And that just works out much better for our calculations. Yeah? But for the moment, we're happy to leave kilonewton meters. Kilonewton meters is the commonly used term until we start doing our calculations. So, our right-hand side, let's have a look at the right-hand side. It looks like this. So we've got M, I've got 2 meters, and we've got 20 kilonewtons. We have the 40, but like we said before, the 40 doesn't really matter. So the right-hand side equals 40 times 0, and then it has, well, this is 20. I've written minus 20. Is it going clockwise or anti-clockwise? Anti-clockwise. So we're going to leave it as minus times 2. So our answer is going to be RHS equals minus 40 kilonewton meters. And so that means that RHS plus LHS, the left hand plus the right hand, equals 0, which is exactly what we expected. So we can say here that at this point it's equal to 40 kilonewton meters, or 40 times 10 to the 6 Newton millimeters. Now, if we go back to our equation here, we said that this formula here is going to equal M at M equals 40 times 4 divided by 4. Well, that's pretty easy. Let's have a look at that maths. Cross out 4 and 4 equals 40 kilonewton meters. Now, I want to remind people that this formula only works, it only works if there's a single force mid-span. Yeah? It only works if it's a single force mid-span on a simply supported beam. Yeah? Now, that is still pretty useful. I would say about half the time the HSC is going to give you questions where it's a single force mid-span. And so you might say, well, why are we bothering drawing these diagrams if we can find out the important M, the M that matters, the maximum M. If we can find out the maximum bending moment, M stands for bending moment. If we can find the maximum bending moment using this simple formula, why would we bother with these complicated diagrams? And the reason for that is this formula only works in limited applications. Okay, so now what we're going to do is we're going to look at this point 1. Yeah? So, or location 1. I had a student this week who didn't get that. So I'm just going to write here 20 just so we can remember. If we're looking at the left-hand side at location 1, I'm going to remove this now because we've done with this and I want to write in the white space. Okay, if we're taking the left-hand side at point 1 equals, okay, so what do we got here? We've got, so the left-hand side equals, I'm going to draw a little diagram. Here, it's 20 times 1 meter times, that's all we've got. Yep, that's all we've got. What is that force going to be? Is it going clockwise or anti-clockwise? Let's start there. Relative to our location 1, is it going clockwise or anti-clockwise? Clockwise. And how many meters away is it from our location? 1. So our answer is 20 kilonewton meters clockwise. Okay, if we look at the right-hand side, let's draw that diagram. It's a bit more complicated. So we've got 40 kilonewton meters, 1 meter away, and then another 2 meters away we've got our reaction of 20 kilonewton meters, yeah? Let's have a look at that. I'm going to write that down a little bit lower, just so I don't run out of space. RHS equals, okay, so measuring from our location, we've got 40. Is it going clockwise or anti-clockwise? Clockwise, and it's 1 meter away. And then we've got the 20. Is it going clockwise or anti-clockwise? Anti, yeah, so it's keeping that as is. And how far away is it from our location? 2? 3. 1 plus 2 equals 3. Okay, so what does that equal? Well, we've got 40 minus 20 times 3 is 60, which gives us the answer of minus 20 kilonewton meters. Or we could write that as 20 kilonewton meters anti-clockwise. Yeah? What happens there is we can say left-hand side plus right-hand side equals 0. Now, without drawing every other point along that line, we can presume that it's going to be looks like that. Now, very, very, very quickly, we're going to do just the left or the right-hand side. We don't always have to do both sides. I'm just proving that it works. If we look at this location 2, right, let's have a look at that really quickly. Do we want to do the left or the right-hand side? What do you think is going to be easier?
Right.
The right-hand side. Okay, so if we take the right-hand side, it's going to look like 1 meter times 20 is going to equal RHS equals 20. Is it going clockwise or anti-clockwise?
Where's location 2?
Location 2 is here. So it's going anti-clockwise. So it's minus 20 times 1 equals 20 kilonewton meters. Important note right there. Now, we can do that. It's allowed to do that, right, and encouraged to do that. But another way we can do that is we can actually just look at the area. So I'm going to just prove this one more time with a very simple equation, right? What we're going to say is here, if we look at this area, I'm going to call this location, or this area 1, right? In area 1, what is the area at area 1?
2 times 20.
So it's, this distance here is how many meters? 1 meter times 20 is an area of 20. Okay, and then we're going to add this area. I'm going to draw that with double the lines, right? Just to make it clear that it's a different area, yeah? So this area here is going to be, again, 1 meter times 20, yeah? So if we add that, what we get is 20 plus 20 equals 40, yeah? Now, here, down here is actually negative 20, right? This location here, this depth, it's actually negative 20, yeah?
Yeah.
So what's the area of this whole block? What's the area of that whole block?
2 times negative 20.
2 times negative 20. So if we have 40 and we add on to that 40 plus negative 20 times 2, like that, equals 0. Does that make sense? 4 plus minus 40, sorry, 40 plus minus 40 equals 0. Yeah? So these are the two different ways that we can approach it. I'm okay with you using the calculation at each point. That's very time consuming. And very quickly you'll find that if you can just find the area under the curve, your life is going to be a lot faster. Now, I have seen different perspectives. I've spoken to engineering teachers, engineering studies teachers, who did not know that you can just do the area under the curve, even though Copeland says so in his book, right? It's definitely much faster for me if you just use the area under the curve. Okay, so that question's done. We're now just going to, as quickly as we can, do the next questions, do the next examples in Copeland's book. So Copeland goes through this in a lot more detail than I have, but I'm just interested in just looking at these questions. Okay. Now, we could find these reactions ourselves, right? We could draw up this diagram and say, given the loaded forces, tell us what the reactions are. what I'm going to do is I'm going to draw the free body diagram. Each of these is 1 meter. 1, 2, 3, 4. This beam is a cantilevered beam. We don't know which one's a pin, which one's a roller. It doesn't matter for us because there's no horizontal forces. If I recall correctly, the syllabus says that you never have to draw a bending moment diagram for anything with horizontal forces. So that's good. That makes our calculations a bit better. We've got, these are our forces. We have a 6 and a 6 down, and we have a 3 that's cantilevered. Cantilevered means that the force is applied outside of the reactions. We have 2 reactions and we have a force that's applied outside of the reaction. Okay, so I'm going to draw that diagram here. We've got a 6, and we've got a 6, and a 3, and they're all kilonewtons. And we have a reaction, and we've been told the reaction looks like this. In this particular case, we could do some of the forces about A and B and calculate those reactions. But that's not our focus today. So, if you need to find out more about reactions, there's a good homework for you is to calculate the reactions. But that's not our goal here. If I know already that this is 10, and I just happen to have covered up the other one, could anyone tell me what is the reaction at this location? How would I solve that? I'd use sum of the vertically equals 0. Forces was what said. I don't think the microphone would have picked that up. Oh, I'm using my arrows the wrong way. Now, I always find with these it's just easier to draw a little diagram. 6, 6, 3. I've got 10 going up. So what have I got here? I've got 12 minus 15, so it means I've got 5 missing. Yeah? So let's write in 5. The answer is 5. Okay. It says up here 5. Okay. Shear force diagrams I find pretty easy. This is a free body diagram. The free body diagram, it eliminates all of the trees and the birds and the people sleeping under the bridge, anything, maybe the people going fishing. None of that matters, right? None of that's part of this diagram. All we care about is forces and the members. Okay, the next thing we're going to do is we're going to draw a shear force diagram. Okay, so once upon a time, remember we always have to start at 0. The left and the right hand sides have to be 0. Because there's no other beam on the left hand side for the things to balance out. Yeah? The idea is that if at any location, and this will be more interesting when we do the shear force diagram this time around. Okay, once upon a time, there was a shear force diagram and we went up 5.
How many do we go across?
Sorry?
How many do we go across? How long is the beam?
Oh, each of them is 1 meter. So, the shear force diagram, she walked across 1 meter. And then what happened is a big scary force, 6 down, came along. And so that 5 went down to 1 kilonewton. It was very scary. And then, so it was now at minus 1 kilonewton. And then, if that wasn't scary enough, another scary 6 came along. And now it was minus 7 kilonewtons. But it wasn't, don't worry. Then the hero came along, and now we went back, we added 10. Minus 7 plus 10 is 3. Then things were going pretty well. The shear force diagram was like thinking life is good, but then something a little bit sad happened, and then she was back to where she started, at 0. Now, I don't know if it's even conceivable that there could be a situation where it doesn't start and finish at 0, but we're going to say at the HSC level, absolutely, it's always going to start and finish at 0. Okay, so that's our shear force diagram. Now, we can draw a bending diagram from that, but before we do that quickly, I just want to point out, I'm just going to do one example of demonstrating that the left-hand side equals the right-hand side. If I look at midspan, point M, let's just prove that the forces on the left equal the forces on the right. Okay, so at point M, what do we have on the left-hand side? We have plus 5 minus 6 equals minus 1, yeah? And if we look at this side, what do we have? We have up 10 minus 3. So the left-hand side at M and the right-hand side at M equals, in this case, plus 10 minus 3 equals, we've got to include the 6 in this case, right? So we have the minus 6 plus 10 minus 3 equals minus 1.
Equals positive.
Positive 1. The idea is that the left-hand side plus the right-hand side equals 0. Yep? Okay, so RHS plus LHS equals 0. The value that we write on this diagram is if we measure from the left-hand side. Yeah? So sometimes if you took the diagram from the other direction, you reverse it. You reverse that sign. So if you started, when we draw our story, we always start from left to right. If we're telling our story backwards, like the movie Memento, well, in that case, we'd reverse our signs. Yeah? We good? Okay. That's all I want to do there. Copeland goes into more detail. If you don't understand what's going on there, read Copeland's book, then come and see me, because that's about as much detail. I mean, I find these fairly easy and intuitive, so I don't, unless you're really struggling with that, let me know. Okay, the next thing we're going to do is we're going to do bending moment diagrams. Okay, so a bending moment diagram, what we're going to do is we're going to take this same story, but we're going to work it into blocks. How many blocks? Well, this is going to be block 1. Do we want to use letters or numbers?
Numbers.
Okay, so this is block 1, this is block 2, this is block 3, and then this one here is block 4. We good? Okay. So, once upon a time, there was a bending moment diagram. It started at point 0. What was the area in that first block?
5 times 1.
5 times 1. Is it positive or negative?
Positive.
So 0 plus 5 is 5. Plus 5 kilonewton meters. Okay, then what happened in the next part of the story?
I went down 6 times 1.
Okay, the area of this block is minus 1 times 1.
Oh.
Yeah, the height of the block is minus 1. It's minus 1 blocks deep, and it's 1 block wide. So where does that put the story? Well, if the story started at 5, 5 minus 1 is?
4.
4. So I'm going to write that here. I'm going to write 5 minus 1 equals 4 kilonewton meters. Okay, then what happened in the story? Actually, I should have written it here. That's where I need to write it. 5 minus 1 equals 4 kilonewton meters. I didn't do any look ahead. See, I said it was a bit smudgy, but it was fine. My students have been telling me about their preferred whiteboard markers. What happened in block 3?
Minus 7 times 1.
Minus 7 times 1. So we're at plus 4, minus 7 is what?
Negative 3.
Okay. Are you okay with that? Yeah, you getting that as well? Okay, so we're at plus 4 minus 7 equals minus 3 kilonewton meters. And then lastly, I don't even need to add this one in, but I'll do it. This one here is 3 times 1. So it's 3 kilonewtons times 1 meter is going to be back to 0. Yeah? My brother, when he was little, he had a bit of a speech impediment, and when he changed the TV, the TV only worked when it was on channel 0.
Yeah.
And we used to go and steal the remote, change the channel, and so that he couldn't watch his thing, and then run away. And he used to say, "Put it back to 0, you moron." Anyway, we thought that was hilarious. Anyway, that's what brothers do. I wouldn't have done it to someone who wasn't a brother. Okay, so in this case, what is our maximum bending moment?
Plus 5.
Plus 5. Now in this case it's pretty easy, but I want to remind you that they're absolute values. Do you know what absolute values are? Absolute values, we don't care if it's plus or minus, it doesn't matter. Yeah? It doesn't matter. Now, for steel in particular, if you're making something out of a regular steel section, right, it's the same section of steel all the way through, we just use the biggest or the largest absolute value, right? Whichever value is the largest absolute value, whichever one is furthest away from the line, that's what we design for. For concrete, it's a bit more complicated. Now, I don't want to go into too much detail here, but some people show these diagrams upside down, right? Some people show these diagrams upside down. And the reason they do that is this. Imagine if you were, this is the way the beam is going to deflect. Does that make sense? That's how it's going to deflect. And what that means is we're going to have tension here and tension here. Yeah? So if we're going to put steel in this beam, if we're going to put steel in a beam, in a concrete beam, we're going to reinforce it. It's not a very good beam, but you know what? I'm going to live with it. we pretty much always put steel all the way through on the bottom. Right? Even if it doesn't need it, we always put a little bit of steel on the bottom. I guess I could imagine a situation where someone would stop the steel on the bottom there. But normally we don't have to put steel in the top. We can, if we need to make a really strong beam, we can add extra steel to both top and bottom. But normally we don't have to put steel on the top unless the top is in tension, in which case we have to put some steel there. Yeah, we have to put some steel wherever it's in tension. Yeah, because concrete is no good in tension. We need to put some steel there so that it can be strong in tension. Now, because our maximum is here, we might add some extra steel in that location. Now, that kind of looks like it's adding an extra row of steel, and we can do that. But sometimes we can squash extra bars of steel in between, and in which case, in a diagram, how we'd show that is we'd just show, add some extra bars in between there. To show you what that looks like, let's just draw a couple of cross sections. So we're going to draw a cross section at A, we're going to draw a cross section at B, and we'll draw a cross section at C. Yeah? So this is what the cross section of concrete would look like at A. I'll make it a little bit wider. At A, we might just have 3 bars. Yep, 3 bars of steel in that beam. Yep. And then at the next spot, at B, what we might do is we might squash in an extra 2 bars. If it gets a bit too squashy, we can go up, right? So alternative is we could say, well, that doesn't quite fit. We could go 1, 2, 3, we could go like that. That's an alternative way of laying it out. And that's why sometimes it looks like 2 rows and sometimes it just has these little lines to say, put extra steel there. And then finally at C, what C looks like is we're back to needing only our bare minimum of steel at this point, right? Maybe just get away with 2 bars, and then we need a couple of bars up the top. Maybe we put 3 bars up the top. Yes, that's our location, our section at A, B, and C. Yeah, and that's an alternative version of B. It's not what's shown here. That would look like a line above. Okay, this is not a sort of thing you're going to be asked in HSC. It's very unlikely, but they do talk about why do we bother with these diagrams? Well, these diagrams, this was a question, let's just say I have some experience with this question, and